In this unit, we shall look at the speed of waves on a string. We shall start by considering a taut string of uniform density. The string is stretched between two fixed points in order to make it tight, and the string has uniform density mu, which is given by the mass of the string divided by the length. We are using SI units, so the mass is given in kilograms and length is in meters. The Greek word mu is spelled mu. I will now draw the string between two fixed points, and then I'll draw the string again with a pulse traveling along it between the two fixed points. The pulse moves with a velocity v relative to a stationary reference frame. Now, we don't have to stay in the stationary frame. It is more convenient to choose a different inertial frame that moves along with a pulse with the same speed as the pulse, so that the pulse is at rest within this frame. Now we can do this change of reference because Newton's laws are valid in all frames of reference or in all inertial reference frames. So as long as the frame of reference is moving with a constant velocity, we should be fine. Now in the new reference frame, all elements on the string move to the left. So a given element of the string initially moving to the right of the pulse moves to the left. So if we consider an element of the string which has a length delta s, we will see that this length delta s is just a segment of a circular path, and so this circle has radius r, which extends to the origin O. So I will draw that again and blow it up to the right so that you can see the entire segment delta s, and this segment delta s is the segment of an arc which is part of a circle of radius r. So this element delta s has a centripetal acceleration equal to v squared over r, and this centripetal acceleration is applied by components of the force T, whose magnitude is the tension in the string. The force T acts on both sides of the element and is tangent to the arc as shown in my figure. The horizontal component of the tensions cancel out, and so we are only going to be looking at the vertical components of the tension. And these vertical components are what creates the centripetal force that draws the segment to the center of the arc. By analyzing the tensions on the segment delta S, we can see that the two tensions T acting toward the center of the circular path each provide a tension equal to T sine theta. So on each side of the segment delta S, we have a tension T sine theta. So if we add these two together, our total centripetal force Fr subscript T would be equal to 2T sine theta. So in analysis of forces, in the horizontal direction, tensions cancel out, while in the vertical direction, the tensions add up. So by analyzing, you will see that sine theta is equal to Fr over T, which is the opposite over the hypotenuse on the right side of the segment delta S, and on the left side also the sine theta is equal to Fr over T. Now, because we have a segment which is a part of a circle, the segment delta S is equal to R times 2 theta. And we also know that the density mu is equal to the total mass divided by the total length. I'm using uppercase M for total mass and L for total length. So because it's uniform density, the segment delta S would have density given by lowercase m divided by the length of the segment delta S. So the mass of the segment is given by mu delta S. Now we can apply Newton's second law, F equals ma, So for the radial force F subscript r, that should be equal to the mass of the segment multiplied by the acceleration a of the segment. The acceleration a is equal to v squared over r, where v is the speed of the pulse and r is the radius. So the centripetal force F subscript r is equal to mv squared over r. So now the total centripetal force Fr subscript t is equal to the sum of t sine theta on both sides of the segment. So that's equal to 2t sine theta. And I'm saying that the Fr subscript t, F subscript rt total is equal to Fr plus Fr for the radial force on both sides of the segments. We can now make an approximation. Because the angle theta is very small, we can say that sine theta is approximately equal to theta, so that the radial force, which is F subscript RT, our total radial force, is now equal to 2t theta instead of 2t sine theta. So applying this in Newton's second law, we will see that 2t theta is now equal to mv squared over r. Let's replace m by mu delta s, where delta s is equal to r times 2 theta, as we found earlier. So we shall see that 2t theta is equal to mu delta s times v squared divided by r. Cancel out your 2's, cancel out theta, and cancel out r, and you are left with v squared equals t over mu. So V is the square root of tension divided by the mass per unit length, or the density of the string. Let's look at an example. So I will read this example as I write it. A uniform string has mass 400 grams and length 5 meters. The string is stretched tight by passing it over a pulley so that it supports a 3 kilogram mass. Find the speed of a pulse traveling along the string. So I've drawn a diagram there showing the length of the string as it passes over the pulley and the mass hanging at the end of the pulley. We know our formula for finding the speed of a pulse on a string is given by the square root of tension divided by density mass per unit length. So we can first find our density mu, which is the mass of the string divided by its length. So that density is given by 0.08 kilograms per meter. Now in the vertical direction, the tension T minus the weight is equal to 0 because the net forces vertically are 0. We are just holding the mass fixed so that it keeps the string taut. So the net force in the y direction should be equal to 0 since there is no acceleration. So the tension is just equal to the weight. So calculating that, we will see that T is equal to 3 kilograms times 9.8 meters per second squared for acceleration of gravity. So the tension is 29.4 newtons. So the speed can be calculated by taking the square root of tension divided by density. And so this is equal to square root of 29.4 divided by 0.08. And that gives us 19.17 meters per second.